All right. Shall we crack into it? So hopefully everyone can see the slide up on the screen. This presentation is going to be a little bit different to Stephen's in the sense there's not so much practical kind of stuff, but when the pack topic came up, I thought to myself, so I'm a dinosaur. I've been doing this long enough that I have to Wikipedia my first project to see when it was. So I think that was about 14 years ago. And obviously the world has moved on quite a bit from then. And, when you've been in technology for a little while, you start thinking to yourself, how much of a dinosaur am I? And am I going to become obsolete? And any of the things that I have learned still relevant to what we need to do today? So if we crack into it, right? So we're going to cover off a little bit about me. I'm going to have a rant about you kids today and all your fancy tools and things like that. And then we're going to have a brief wander into a sense of impending doom for me as a 14-year performance tester. So, about me. This is me. When I was growing up, there was a TV series on here in New Zealand. It was a Jim Henson series, and it was called Dinosaurs. And I always kind of identified with B.P. Richfield, and I particularly identify with him now because, he's this angry dinosaur. He's the boss kind of thing. And it seems appropriate because I started performance testing way back last millennium, if we want to go that far back. I had a bit of a development background, so you'd think that would be a little bit of a natural fit for performance testing. And as it turns out, it really isn't. It's helpful for when you learn how to use a tool. And as performance testers, that's usually the first thing we do, is learn how to use a tool. But the thing about having a development background is that often it doesn't teach you that the fix for the present situation might actually cause even bigger problems later on. So bearing that in mind as a developer, just because you can code doesn't mean you understand architectures, it doesn't mean you understand queuing theory, it doesn't mean you understand how to think long term. So this brings us to my little bit of a rant, you kids today. So when I started out, we had very few things in the ways of APM tools. The performance testing tool, LoadRunner, was kind of the tool back then, and you had Rational on the other side. We didn't have a lot of really, really fancy stuff to help us go through. So I went for a job interview at one place, and one of the performance testers, who was older than I am, said, "Are you comfortable building your own tools?" And I lied, and I said yes, and turns out actually I wasn't. But throughout this presentation, we're going to come back to that theme, and we're going to come back to the theme of the more things change, the more they stay the same. And particularly for a dinosaur guy like me, who spent a lot of time learning from these things, these are books that are like printed out bits of the internet, printed out bits of Stack Overflow. This one's very good. Capacity planning, lots and lots of books, and you think to yourself, so how obsolete am I? Because we're in a brand new world now. We've got artificial intelligence to help us tune. We've got APM, which is meant to solve all of our problems. And we have the genesis of this topic, which is someone who said to me once that auto-scaling is going to make performance testing obsolete. So we're going to dig into that a little bit. And the way we're going to dig into it, funnily enough, is going straight back to the past. So we're going to look at a batch process. And you think to yourself, well, the batch process has nothing to do with the cloud. And by itself, it probably doesn't. But we'll get to that towards the end of the presentation. And I'm kind of hoping by the time we get there, you'll know where this is going. So this was my system. This was the thing that I had to test. It's a batch process. We have 3 main batches, one of whom is called main, another one is called claim, and another one is called generate. Main goes through a database, it picks up a whole lot of payments that has to do something with, it does something with them, it writes it out to a staging table. The claim batch process picks it up, does whatever it does with them, changes a flag in the staging table, and the generate process finally reads stuff out and spits it out to one or more payments files. Now, batch testing is kind of very old school. And it's not something that people often think a lot about. How do I performance test a batch? But the interesting thing with them is batches are bound by a resource envelope. You only have so much compute that you can use. They're definitely bound by time because we have to get the batch through within a specific period because we don't really want them running into business hours because, batches, they're pretty processor intensive. That's why you batch them. You want to give them as many resources as you can for as long as you can to let them go. But there's a couple of very, very interesting things about a batch. And the first thing is you won't have a tool. You might have a scheduler that will kick off the batch, but you won't have a tool to help you do any analysis. That sort of stuff you're going to have to build yourself, and it's going to be a lot of digging to get into it, but it's a lot of fun to do so. The other thing, you're going to be dealing with a lot of data, and none of that data is going to be consistent. You're going to have timestamps in different formats and different time zones. You're going to have logs in different formats with different limiters, different character sets, all these sorts of things. Smaller batches, even little ones, are going to generate potentially millions of rows of data that you can have a look at. And most importantly, a batch is just like any other performance test. Batches have concurrency. Batches have arrival and completion rates, and batches have wait and service times, just like a web system. You just need to think about them a little bit differently. In this instance, we're quite lucky because with our main batch here, we can configure how many instances of the batch we're going to have. We can do the same with the claim batch. We can do the same with the generate batch. But there's one thing that started to bug me about this project right from the very beginning. We've got a nice yellow arrow saying back off. Now, back off, it's almost like the AWS exponential back off, but not quite as clever. Because instantly we can see if we have more than one thing hitting this table and grabbing the same amount of records at the same time, we're going to get some locking. So when locking occurs, the system goes in and backs off for a random amount of time that you set. So it could be sort of like 5 seconds plus or minus 1 second either way. And the idea for that is that it releases the lock, and the next time the batch process comes around, it can grab a new set of records. So instantly, that's ringing alarm bells for me. And the reason it's ringing alarm bells actually goes back to 1967. And this is one of those things that I wish I had known. Once upon a time, when I first started, somebody said to me, Scott, you're never going to be any good at this job until you understand queuing theory. So that was 12 years ago, and I've spent a lot of time learning queuing theory since then, and it's fascinating stuff. It means you don't get bored at the supermarket checkout, for instance, and that's kind of handy. But when you start learning the foundations of queuing theory, you realize that there is a lot more that you have to learn, and you start moving out into the scalability laws. So back in 67, Gene Armdale, he worked for IBM's mainframe division, came up with this theory, which is now a law, that applications can execute in 2 different modes. You have a part of the application that can execute in parallel, and you have a part of the application that absolutely must execute serially. So by serially, we're waiting for a resource to be unlocked. So that could be a disk queue, or it could be a lock on the database table. So from this diagram here, what we've got, where we've got row equals 1 at the top, that's our application, our hypothetical application. That can be broken up into bits which can be executed in parallel and bits that can be executed in serial. If we go to row equals 2, we get a performance gain. So the overall execution time shrinks, and that's a good thing. We like that. If we go to row equals 4, we get no benefit because all of a sudden our serial part of the code is dominating our execution time. So we could go up to row equals 10, 12, 20, 30, 40, 50, whatever it'll be. And we're not going to get any discernible impact, net benefit impact of that. Now, when Armdale came up with this, basically he was trying to show that a very fast uniprocessor can often handle work much more efficiently than multiple parallel processors. Now, he kind of lost out on that a little bit, in the sense we now have distributed systems. But the irony is that this law is now more applicable to those distributed systems than it probably was back in the mainframe days. So the nice thing about Armdale's law is it gives me a little bit of framework to work on, but I'm also aware that there's another law over the page. Armdale's law, in my case, represents the best possible scenario, that the more resources and the more parallel instances I add to my batch process, I'm probably not going to get any benefit. The other law that comes into play, which was one of the textbooks I held up before, is the Scalability law by Neil Gunther. And this is, I think, 1993 vintage, so comparatively new compared to Amdahl's law. Now, what Dr. Gunther suggested, and I have seen this hold true in multiple scenarios, quite varied scenarios, is yes, we accept everything that Gene Amdahl said, that there is a serial component in the code. But there is also an overhead when I start scaling out multiple parallel things, because I've got inter-process communication. If I'm thinking about processes, I've got cache swapping and things like that. When I think about my batch process, there's a lot of things going on between the instances. And spoiler alert, I never actually found out which one was causing the additional overhead, but it does exist. So what this law says is the more parallel things I add, the slower it's going to get. So things can always get worse. Now, if we think to a cloud and we think, well, we'll just spool up a whole lot of instances, the same thing applies to that. Adding more stuff doesn't necessarily make things better. It can, in fact, make things worse. Which brings us to this wonderful quote. And I know James Pulley uses this a lot, and it's one that always rattles around in my head. Like him or hate him, I think this quote by Donald Rumsfeld, anyone who has been in performance for more than 2 years will sit there and think to themselves, yeah, I actually get that. I know that there are known unknowns, and then I know that there are unknown unknowns. The key to having, I believe, a good foundational framework for performance testing based on the fundamental laws, queuing theory, scalability laws, is it helps you define and create a conceptual framework for what some of those known unknowns are going to be. And then that lets you focus on the unknown unknowns. So it sounds a little bit trite, but we'll work through it, because the example that I'm running through is just one project that's pulling in all of the stuff that I wish that I had known when I started out, and they're applied to this as we go through. So we run our batch processes, and the good thing is we can control how many batches we have, which is nice. You know, you often don't get that level of control. We don't have a tool at all. We don't have an APM tool. We don't even have JProfile. So we have nothing except access to the Linux boxes they're on, a decent amount of permissions to go and have a poke around in the directory. We've got Perl, we've got R, and we've got a timestamp in the database for when something happened to the record. So, in good experimental fashion, we start running each of the batches with a varying number of instances. So where there is a dash is where I don't have data anymore. One of the reasons why this isn't necessarily a live demo is the data is inherently sensitive. It's insurances, it's claims, and it's things like that. But if we have a look at how we've scaled out, we can see for our main batch anyway, 2 instances in terms of transactions per second. Actually looks pretty good, right? And so we've got 3.5 TPS. We go up to 4 instances, and that drops quite precipitously, very, very quickly. We go up to 8 instances, it drops even more. We go up to 16 instances, it drops even more. And let's just ignore 24 instances, because that shouldn't happen. Should. We look at the scalability laws and we think to ourselves, there's no way that should have gotten faster when I added more instances. If anything, it should be roughly the same as 16 instances, maybe. Because I'm adding more resources, so something's gone wrong. We look at the other batch processes, and again, the claim, 4 instances, looks pretty good. And for generate, well, you know, in all honesty, none of those look particularly good when you think about it, but at least they're not massively varying. From memory, optimum that we went live with was 2 instances for main, 4 for claim, and I believe it was 2 instances for generate. But all things considered, this is a nice, neat proof for either the scalability law or Amdahl's law, apart from 24 instances for main. Now, we could ignore it and we could go home, but there was just something about it that didn't add up and didn't make a lot of sense to me. So why is it? And incidentally, why haven't I mentioned the cloud yet? Because, you know, cloud's meant to be in this, but, you know, we'll get to it eventually. So, going to what Stein always likes to mention, go back to the data. Go back to the raw data. Now, again, we have no tool at all. So the best thing we can do is have a look at the database, see when something happened, or because I'm a naturally inquisitive kind of person, we start digging into the logs. Now, the logs for this batch process were actually really, really nice. So they had what's referred to as a steel thread or a golden thread. So it's a unique identifier that stays with a transaction through its life cycle. Not only that, the steel thread told me when something left for processing, when it came back for processing, how long it took, and what the status was, as well as the message. So that's good. I've got these really, really nice logs, gigs and gigs and gigs of them, but Perl can deal with that. Fortunately, I have R on hand because I don't use Tableau anymore because everything else I can do in R, and I kind of like Linux, so I like something to run on Linux. And with a little bit of Perl scripting and some very, very simple R, I can plot out my response time. So each message has a response time, or it's actually, to be technically correct, it has a service time, the amount of time the system has spent servicing the request. So in a batch process, what we would often like to see would be a nice flat line, some variation in it, right? But generally we want it to trend across. So if we're going to process, say, 3 TPS on average, on 1 second it might be 3, on the next it would be 2.9, on the next 3.1, or whatever it is. But things will hover around that mean. What we don't want to see in this case is a little fuzzy caterpillar starting to walk up the screen and then just completely disintegrating towards the end of the run. So the blue on the screen represents my main batch. The green and the red represent claim and generate payment, and we don't necessarily need to worry about the other ones at this case because main is the one that looks like is going to give us a problem. Now, the issue is that we only have a few hours to run this through. So even best case scenario, this thing is not fast, and chances are we're going to blow through our window anyway. But we'll get there. So we plot it out, and it looks bad. But this is the second thing that I wish I had learnt and known when I started. There is value in building your own tool set, and nothing forces you to do that quite like a batch process. When you build your own tool set, you start looking through the logs, you start seeing patterns as you're trying to figure out how to parse them that you might not otherwise see. And in this case as well, even though we were trying to get JProfiler and things like that in, it was going to take time because you're working in a corporate environment. Even $100 needs to go up through whoever it is to sign it off, and then you need permissions to install it. So it was just quicker, in all honesty, to start working for our own thing. But the question is, with this one, why is it getting slower? And why are things disintegrating at the end? So you think to yourself, well, I know from Amdahl's law and from the scalability law, if I'm getting sequential locking in the database, if more than one of these processes are trying to hit it at the same time, maybe, just maybe, I'm wasting time with those locks. That serial dependency is coming in for me with the main process, and it's really, really hurting me. So I turn to what is already been mentioned, I think, on the PAT, which I refer to as the world famous tornado chart. Now, this one is a little bit small, and it's small for a reason, because the thing I was expecting to see, I didn't see. So we've got 3 batches here: claim payment, generate payments, and main. Now, with the tornado chart, the length of the bar determines how long something is happening. They're very, very good to see concurrency. The more bars that you start seeing lining up together, the higher the concurrency is, and you can start making some extrapolations on that. The more of these processes line up together, the worse things are happening. And we can see from claim payment and from generate payments that actually there is some of that happening because we've got these little longer bars. When we look at main, there's nothing. We've got a couple, but it looks almost like a standard scatter graph. There's not much happening there. So it's a case of, well, I don't understand, because the other 2 batches are performing exactly as I'd expect them to perform. If we have multiple things hitting this table at the same time, we can see little purple bits on the graph. Those are the thread sleeps. So that's when a lock has been detected, it's gone away, it's had a sleep, and that's contributing to the overall runtime. It's just not there for the main batch. So I don't know where we're losing time. It doesn't look like we're bound in the database, because in fact the database stats during these runs are doing virtually nothing. Now, if I had an APM tool, for instance, maybe I could start drilling into the JVM, but I don't have an APM tool. And in fact, the way the batches are written, rather dubiously, is that each batch is its own instance of its own JVM. And they are only started when the batch runs, and then they get killed. So instrumenting that with an APM tool is quite difficult. And while this was going on, our APM vendor was in there trying to figure it out, but they couldn't. So again, it comes back to a case of, you kids today with your tools and stuff like that. Well, here comes the Dinosaur, and I've got some logs, and I've got some Perl, and I've got some R. And I'm also running on Linux. And Linux is really, really great because it does lots of things that Windows doesn't necessarily do. And particularly Red Hat with OpenJDK on it has got lots of nice little tools like JSTAT and things like that. So because I got on quite well with the developer, we could get in and we could change the startup for the Java app, and we could get it to start writing out GC logs. And if we take the GC logs for two of our main processes, doesn't that look familiar? So the top, towards the end of the batch, we are spending 12 seconds in garbage collect. A lot of garbage collect. And we're spending 12 seconds in garbage collect a lot of times. If we look towards the end of the graph, we can see actually that's pretty much all we're doing is garbage collect as this thing's running. So it gives us a little bit of a clue. So again, we've got to this point with no tools, apart from the stuff that we've figured out ourselves. So we look at that and we think, this is just really, really weird, because this doesn't explain, for instance, why when I go up to 24 instances, things get faster, because it shouldn't. If everything else is getting slower, why do we get faster at 24 instances? But we're starting to get some clues. So we go off, and we have lunch, and we go for a swim, and we come back and we think to ourselves, I'm so used to looking at data in terms of test time versus response time. I wonder what would happen if I take every single run of the batch that I've done, and I just basically determine how long something spends processing and how many things that it processed in a batch. So if I just put the number of records across here and the service time up here, I wonder if that's going to show me something. And here it is. Now this is quite an interesting graph. This is all of the main runs that we did over however long we were on this project. All of this was done in R. It's just a case of dropping it in, telling R, pivot the data, assign an integer value to each one, so a group and a summarize, and plot it out. So at the beginning of the run, when we're doing sort of like 0 to 10 records or so, things are slow. It's Java. Java takes a little while to actually spool up and do all of its Java-y things. So that was kind of expected. Things get faster, but we have this trend of processing time going all the way up until we hit about 1,000. And then things go absolutely ballistic. We're looking at sort of like 25 seconds to process each record. For a batch, that might as well be 100 years. So, what do we do? Then, funnily enough, after we go past, say, 1250, things get faster again. So that doesn't make a lot of sense either. Which brings us to one of these very, very interesting conversations that you often have as a performance engineer, usually before a crisis meeting. And you talk about this with the Linux systems admin. And the Linux systems admin said, well, that last run that you didn't actually complete because the kernel issued a kill command and stopped it. And I think that's a very interesting. And so we go into Linux and we have a little hunt around inside the kernel. And sure enough, having a look at the kernel logs, there was a kill command issued. But the kill command wasn't issued by the operating system. The kill command was actually issued by the wrapper process that ran it, going back to that first diagram. What's happening, as the batch is running, it trundles along and then it starts getting into this garbage collect period of doom. While it's doing the garbage collect, it can't respond to a message that is getting sent by the wrapper to the batch, which basically says, are you okay? Because it can't respond to that, the wrapper issues a kill command brings down that batch instance, and then starts it up again. Because the batch instance is started up again, there's nothing in heap, there's nothing in memory, so it actually starts out with a clean slate and then starts getting slower and slower and slower as we go. So, interesting little fact, but it still doesn't necessarily explain why, when we get to 24 instances, things get faster, except there's a little bit of a gremlin in our application. When we get to 24 instances, we have less records per instance. So we spend less time in garbage collect, which is a good thing. We do spend more time getting bound in a service layer, but because we were running less instances with a larger amount of record set, we're spending so much time in garbage collect that starts to dominate the execution time. So we've got a choice. And our choice basically is we can have the optimal number of instances, and we can assign a stupid amount of heap memory to it, like 20 gigs per instance. Or we can fix the code, make sure it doesn't enter full garbage collect, and run with our optimal number of instances. So the answer basically is, I can leave up to you for this one, but you can probably guess, do you provision a machine with 50 gigs of memory to run 2 instances of this batch with a little bit left over, or do you fix the code? And the answer is, well, there's a machine there with 50 gigs of memory in, so you have to figure it out yourself. But the key takeaways from this, even though it is a batch, and we're going to get onto the cloud in the very, very next slide, is the foundational principles allow you to have a structure to understand how something is working that you might not otherwise have. Learning to build your own tools for analytics helps you understand the architecture of the application, helps you understand what the logs are, and it makes you see things that you wouldn't otherwise see. You'll see warnings that you weren't expecting, you'll see errors you weren't expecting, you'll see normal things that you weren't expecting that just take a lot of time. And the third thing was, when I started at this, I was limited to what the tool or the tools could do. If the problem space existed outside of that, then I had nowhere to go. So figuring out how to do stuff for yourself is very, very important, which brings us to the final set, a sense of impending doom. So if we go back to auto-scaling makes performance testing obsolete. So first of all, in the instance of our batch process, auto-scaling is not going to help me. It's not going to matter how many of these instances I throw at this batch. Bad code is bad code. It honestly is not going to make any difference. Secondly, scaling is hard. It's a very, very hard thing to do, particularly when you start getting down to database level. Now, in our instance, and I think probably a lot of us here would have been through this, one thing that often gets sold in terms of a cloud migration is a lift and shift approach. So let's take our batch process. Let's stick it up in the cloud, because then we can scale it vertically, and we can add more CPU, and we can add more memory, and we can do all of these very, very good things. That's not going to help the database, but never mind. In this instance, it's unhelpful, and it's a bad anti-pattern to start getting into. So one of the things I've often said is I don't hate the cloud. In fact, I think the cloud is quite a good thing. What I do hate are cloud vendors who say that it's going to solve all of your problems, when in all honesty, it's probably cheaper just to fix the software. Now, talking to someone who says that auto-scaling makes me obsolete, I can explain mathematically the principles why that is not going to happen. I can go through Amdahl's law, I can go through the scalability law, I can give Gustafson's corollaries to that, which frankly I haven't really seen in practice anyway, but it's a nice idea. But I thought to myself, being the dinosaur that I am, can you teach an old dinosaur new tricks? Turns out, with enough time, the old dinosaur can learn some new tricks, because I thought from my point of view as a performance engineer, an old performance engineer, it would be interesting to go to the source. And part of that was, why don't I certify myself in AWS? I had support from my employer, which was great. I started off the cloud practitioner, and then I moved up to the solutions architect. Now, the great thing for me as a performance guy, learning the AWS stuff, and Microsoft's Azure, I assume, is going to be the same, because I'm starting to go into that AWS believe that performance testing is at the very heart of everything you should do in the cloud, because you should be following their best operationally excellent principles. Everything you do should be infrastructure through code, which means you can spool up your environment and then spool it down, so you have no excuse not to performance test. The other very, very interesting thing to come out of the certifications is scaling a system is hard. Systems need to be architected to take advantage of it. So making your application layer stateless, for instance. Now, I don't know how many architects I have worked with in an organization who have taken the lift and shift approach would even understand what that meant. But from our point of view, we're usually used to dealing with systems that are based on premise. So you come in and the cookie says you go to this server and you go to this server for the duration of your session. In an auto-scaling world, that server may or may not exist from minute to minute. So you need to design your application around that. And even if you can do that, if scaling an application layer is hard, scaling a database layer is very, very hard, infinitely harder than scaling your application layer. You've got to consider, am I going to be using read replicas? How am I going to keep data in sync across all of these? Do I need to shard to start taking care of writes and all of these other things? Because at the end of the day, even if you're in the cloud and you have a situation like that, we still have a serial dependency, just like we did in our batch, and just like Armdale suggested way back in 1967. So my knowledge is not obsolete. When it comes to the AWS stuff that I've learned, the knowledge forms a nice, solid, foundational understanding of how cloud scaling works, as well as how application scaling works on premise. So my recommendation is for anyone getting into performance, learn some of the fundamentals first. It's going to be a massive, massive help to you if you spend even a week going through queuing theory textbooks and getting your head around how this stuff really, really works, and embrace the dinosaurs that have come before you. Stand on the shoulders of the dinosaurs that have come before you. Take what they've learned and apply it to what you do now. And that is me. All done.
Thanks. Yeah, thanks. Awesome. Thanks for the presentation. I had to stand up and look at the screen because I'm looking at the T screen, at the detail of the graph, because there was so many things interesting in the graph, and I said, it's too small.
Those tornado charts are the best visualization in the history of visualizations, I think. If you want to see what the effect of more than one thing happening at the same time is, tornado chart all the way. And in R, they are trivial to do, absolutely trivial.
And I would be super interested. I mean, I know it's not the part of the presentation, but you showed us the tornado graphs. To how complex was it to build those graph through using a data source and R to provide the data the graph that you showed us with the tornado graphs. How complex is it?
Yeah, it's very, very simple. I think in terms of, Stephen mentioned it before, that R in some ways might be easier to use than Tableau, and in this case it is, because R, unlike Tableau, which is sort of like more BI and things like that, R is about data wrangling. So when I have a situation where I've got a whole lot of response times, I can pin a column in R and I can get it to rotate everything else around that column for me. And then I've got a start time, end time, and a duration. I can assign a unique identifier all the way down, or in this case, I've got a golden thread. Bang, away you go, and you just drop one of the axes. So you don't see the golden thread stuff. It's very, very simple to do. I'm probably faster in R now than I ever was in Tableau.
So you're saying that R is simpler than Tableau. So why is Stephen is investing so much in Tableau then?
I don't necessarily think R is perhaps simpler. R is excellent if you're willing to learn another programming language. And if you're willing to put the time into learning it, then being able to share code with people, because code is your thought process. So I can share the R stuff that I did for the batch analytics with everyone else in my team, and they can pick it up and they can run with it, and they can see what I'm thinking and how I did stuff as I went through. There was a lot of Perl backing this up. And I know Perl is another one of those dinosaur things because all the cool kids use Python and stuff like that. But I have yet to find anything that has better regular expressions than Perl does. And you just know them off the top of your head. So there's part of extracting the data out of the logs, then wrangling the data in R, and then doing the plots in R.
Right.
I still like Tableau. I still definitely like it, but since they changed their licensing model, particularly in a consulting situation, it's kind of a no-go. It's just easier for a lot of clients to get R installed and run with it.
But yeah, I think Perl used to be quite a strong language, and I used to do Perl scripting a few years back. I think I almost forgot everything. So
yeah.
I think
one of my go-tos in Perl around the tornado graphs in particular was I always used to get Perl to do the data rotation for me. So I'd take the data out of the logs, I'd find that unique identifier, I'd use that as a hash key, and I'd start loading things into the hash. And I found that every time I needed to do that, I needed to Google how to do a hash in Perl because I could never remember. And then one of the texts I've got sitting next to me in R, it says, well, you rotate data by using this command and saying hold this column and then rotate everything around it. And it was a game changer because it was faster than anything I wrote as well.
Yeah, so I'm pretty sure that you, now, because Python is has so many libraries and available in the market, I'm pretty sure that people can achieve what you described pretty simply with Python. Stephen,
I reckon they can.
What are you using, Stephen? Is it Python or is it something else to manipulate the data?
All the office or the organization in New Zealand that I'm working in primarily is Windows.net, so I use PowerShell now because I don't have to install anything. It does the same thing, right? It's just a scripting language.
Yeah.
I occasionally use Python for things, so yeah, mainly PowerShell. I was just going to say on the point of why do I use Tableau, probably just because that's what I know, but the one benefit I have found is because there are hundreds of people in my organization who use Tableau. There's like a whole support team, Tableau, so I can call them up and they show me stuff I didn't know how to do. Oh, that's really cool, and team out with Tableau server and all that good stuff. Yeah.
And I like the software. Again, it's just if you're kind of funding it yourself, $70 per month US, it's like I need to find something else. It's unaffordable. So, and I've transitioned to Linux for pretty much everything.
Yeah. One question that I had is more related with the batches, because I know that you mentioned moving to the cloud. A lot of people use. I agree with you. There's a false a message that is shared by cloud providers saying that cloud will bring you hot coffee, fresh milk, nice cheese, good wine, and good whiskey at home, and you don't have to worry about it.
Beer on Friday.
Yeah, that's correct. So I think that's clearly something that is not true, and I think especially in the fact that bad performance, they are taking advantage of bad code or bad application because more nodes.
Because in this instance, the cloud potentially could have saved money. You could have had a scheduled reserved instance that came up to like 8 o'clock in the evening to 5 o'clock in the morning with an insane amount of memory, because that was the solution to the problem. For main anyway, 2 concurrent batches was optimal, but each one of those needed 20 to 30 gigs worth of heap to stop it going into full GC. So hence standing up this box with an insane amount of memory to get it through within the batch window. Now, you could have deployed that on the cloud, and you could have said, I want one of these for 6 hours from here to there, and then bring it down. And that might have saved money. But the thing with the batch is the data structures potentially were going to change. So it turns out probably what it was doing is sucking everything out from the database, building this massive, complex, nested data structure in memory. And every time it had to do something, it would trawl through this data structure. So if that data structure changed, then 20 gigs of memory probably becomes 30 or 40 or 50 to get it run. And again, it's that case of, do you provision an insane amount of cloud resource or local hardware in this case, or do you just fix the software? But because it needed to go live like yesterday, it was a case of we'll just provision a whole lot of memory, and away we go.
But you mentioned a lot of batch testing, and do you think that with the help of the cloud, I mean, I'm thinking of Netflix, for example, where they have servers that will serve the users, and while they have those servers serving the media and so on, they have other servers that are here to process batches to parse the new movies and so on. So there are in parallel real users, and on top of that, the batches running. Do you think that this is going to be more and more? Because back in the 10 years ago, 12 years ago, most of the batches were planned during the night to avoid any impact on the system. Do you
and
see
give them as many resources as you can?
Yeah, and do you see any changes by moving to the cloud, where now we are going to run a lot of asynchronous tasks while users are interacting with our system?
Yeah, so I think definitely that's where things will go. But I think the paper that accompanies this, it kind of hints at the idea that all of the stuff around the cloud doesn't actually get us around those fundamental laws. It just masks them. It shifts the problem from one place to the other, and it helps give you a smoother ride across it. So if you can move your batch processing off to the side during the day and have more resources sitting here to service inbound user demand, you still have those sequential dependencies in your batch. It's just they're not impacting your users because you've partitioned all the way down. Now, whether you need to tune them to the extent that you do on-prem, where you've got that batch window, very much, I guess, depends on how long you want that cloud instance to be there for, how much resource you've provisioned for it, because it's not free. Even when you're looking at 2 cents an hour, that stuff adds up over the course of a year. So there's still an impetus, I think, to try and make your code and your processes as efficient as possible. But one of the other things I've noticed anecdotally, particularly when we start talking about cloud, and again, this instance kind of hints at it as well, that it allows you to be lazy, I think, in terms of your development. If you're a dev and something like that, it's like, yeah, sure, we'll create this massive nested DOM in memory and we'll put it up on an EC2 instance or an Azure instance, and we'll just triple the amount of memory because that's easier and cheaper than doing it properly. And again, that's good for right now. In a year's time, who knows what it's going to look like? You might need to double or triple that memory again. In 5 years' time, if it's still running, you might have to do something even more insane, like have 3 or 4 of these, and they're just all memory-intensive machines. So it definitely helps, but I don't think it addresses the fundamental issue that bad software is bad software, no matter how and where you run it.
Yeah, that's true. But I was thinking more about combining, let's say, a test where you have real users, and then suddenly after the 30 minutes of test, you say, okay, now I'm gonna launch the patch, and I'm gonna also measure how many tasks is he able to treat during that period of time, how long is running. And also, I'm interested in see, okay, is there any negative impact by combining real users with my batches, or my users?
Oh yeah. And we did do that, and it was grim. It was not a pretty sight. So the users were massively impacted. So while there wasn't a lot of overhead on the database, there was a lot of overhead everywhere else, because why not put the batch on the same machine that one of the applications is, because that's a good idea. It was grim, and we also discovered through this a poison pill. So it was a functional defect that had massive performance issues, because the way you set up the payment, there was the intuitive way of doing it, and there was the right way of doing it. And if you did it the intuitive way, the batch would crash, and then it would bring down the rest of the system. And it would sit there crawling along for 10 hours, and the system was just totally unusable. The fix for that I didn't know you could do this with the Netscaler, but apparently you can. The user action which caused the downstream batch process took so long to do from the UI point of view, the Netscaler killed the connection. So the data in the database was in an indeterminate state. So the batch would come along, run, hit something it didn't know how to deal with, and it would try to fix it itself, as opposed to writing it out to an exception log and someone deals with it the next day. So the fix to that process was to increase the Netscaler time out to 6 hours. So then if someone did it the intuitive way, then it had 6 hours to complete from the UI point of view, so it wouldn't impact the batch further down. But short answer to the question is, if the batches were running at the same time user actions were happening, it was not pretty. There were locks all over the place and things like that. It was pretty grim.
Yeah, I'm thinking about that because even if you don't have real users, now people are, there's a big buzz on the RPA, robot process automation, where you can automate business process to validate or whatever. So there's a big chance that those robots will run out of the business hours potentially. So I think that could be a case where maybe before I sign or I say, hey, let's do a lot of robots, so we're gonna be more efficient. Maybe it could be worth to combine RPA testing plus testing the robots plus testing the batches, because there's could be a potential window where they're going to be running at the same time.
I've worked on one client where there was overlap in the mornings, and in those mornings it was pretty grim, as the user load and the batch load was still, one was coming on, the other was tailing off.
So I saw that there was a questions from the audience, but Stephen just answered to that. So thanks, Stephen, again. So Stephen is going to be going to follow us during 24 hours and answer to all the questions. So I'm pretty thankful for that. Otherwise, Stephen, do you have any questions for Scott or Arinder? Do you have any questions?
I don't have a question, but more of a comment around what Scott mentioned, like APM tools. I have a situation currently, my place, where we can't use APM to monitor one of our components because it's not supported.
Yeah.
So you can use native monitoring, or you have to create your own logs and pass that.
Yeah.
Another bit is a couple other things. The concept of universal scalability and queuing theory. It's quite useful. You have to learn those concepts if you're
absolutely. Yeah, and it's something a former colleague of mine said as well. And it took me sort of like 3 years to actually start learning that stuff. And I think from my point of view, it's actually made the job a lot more enjoyable as well, because it gives you a framework to hang some of those unknowns off of. Like, as soon as someone showed me the config for this batch and it says, well, there's a back off in case, two things hit the database at the same time. So I know what's going to happen here. At least I've got a fairly good idea that it's going to fall into one of these two categories. It just depends which one it's going to be.
And so maybe, Scott, could you push some links to books that you would recommend to our community if they want to start learning about queuing theories or laws or whatever it is? Do you have any books that would be well explained and that will allow someone new to performance to understand those laws? If you have any of those recommended links, that will be great to push them in the chat. So then
I shall put them in the chat after this.
Cool. Now, this is a book I know because it's been recommended several times by Alexander Podelko, who will speak later today. So it's a great book.
Are hard going because I was never a mathematician at school, so I found them quite hard going. But when the first couple of things clicked, everything else just clicked from there. and particularly now where you can actually see the stuff in action and experiment with it, because they're theories. So using the scientific definition of a theory, they're backed by evidence and they're backed by experimentation. So you can create your own experiments to investigate. So it's what makes it a lot of fun.
Yeah. One of the books, or the author that
There's a dinosaur. At Stephen's house, there's a dinosaur.
yeah, all one. I still look at the Neil Gutner's book.
Yes, yes.
That will,
I had the one with the jet ski.
yeah, I've got that one as well. There's another one with the PDR or something else it's called. Yep, that's the one. PDQ. Yep.
Yep. Well worth a read.
All right. So, do you have any other questions, Stephen? Do you want to add something?
I was just going to ask, oh my God, the cat. What's the what is your algorithm for queuing at the supermarket checkout? It's something I'm also familiar with.
It depends on the type of queue. So it depends if we've got multiple checkout operators and one queue, or multiple queues and multiple checkout operators. Because multi-queue, multi-operator is a lot easier to do in your head. One queue, multiple operators, quite hard to do in your head. There's a derivation of Little's law.